That's from 17. Not what I meant to do. Drummer. Couple things before we get started. Attendance form. Yeah, leave them right. All right. Sorry, I forgot this. Hey, fill this out. Yeah, you might I don't know. You might have noticed I haven't updated the attendance on Canvas recently. You shouldn't worry about it. I have been back to not really the things keep laying it out. I will update it eventually. Again, it doesn't really matter for this class. So even if your attendance grade was 0, you should be like, I don't care. It's not important. Even if it's wrong, no big deal. The other things I actually want to say were 1, midterm 2 this weekend. I posted practice materials there on Canvas. There's like 2 or 3. I think there's 2 old exams and a review sorts we will review on Friday. And we'll be due on Sunday evening as before. You have 100 minutes to take it, upload it, all that good stuff. It should be very similar to the last exam as far as the way it goes. So if the last one was, it made sense last time, it should make sense this time. Something else about that. I think that's all. Also, as far as next week is Thanksgiving. We don't have class on Thursday and Friday. We do have class on Monday, Tuesday, Wednesday. I will certainly be here teaching class on Wednesday. If you want to come virtually, that's fine. If you want to watch the recording later, that's also fine. But I will be here teaching class as usual, so feel free to come if that works for you. But if you already have plans to travel, totally okay. Also, I just found out, I'm totally kind of inside. I guess I didn't know this, or maybe it's something relatively new. Unitrans runs a shuttle from campus to the Sacramento airport on the Wednesday before Thanksgiving, which is kind of cool. I was like, oh, that's neat. So if you're planning on flying on Wednesday, then there's a shuttle from campus to the airport, which is great on Unitrans. There's also the YOLO bus, which goes to the airport in general, but I think the shuttle with Unitrans is like a direct route. So that's kind of cool. I didn't know. I don't think we had that when I was a student here, but you have it now, which is great. Any questions before we? Oh, I know what the other thing I want to say was. So the midterm will be covering all the material up to class S. So none of the trigonometry stuff we covered on Monday or that we'll cover today, just so you're all aware. So it's all the stuff we've been doing since the last exam. Yeah, that's what your question was. Okay. I mean, certainly it is cumulative in the sense that the stuff we have done since the first exam still kind of plays into the stuff we have done after that, but it is more focused on the material that we have covered since exam one. But most math classes, your exams are cumulative in that way, typically, in that you're still building on the prior stuff we've already built up. So kind of works that way. All right, I've ordered new pens, but they haven't come yet. So hopefully my pens keep working still. Let's talk about class U, the unit circle. Really, class U and class V are both the unit circle. I feel like class V is really more the unit circle class, but someone saw the letter U and they're like, I'm going to try and make unit circle work with class U. It starts with the letter U, but whatever. So last time we talked about some special triangles. We talked about some special angles, specifically the angles pi over 3, pi over 4, and pi over 6. Or you might think of them in degrees as pi over 3 equal to 60 degrees, pi over 4 equal to 45 degrees, and pi over 6 equal to 30 degrees. Definitely encourage you to keep those relationships in mind, because we do go, even though I've said and continue to say the calculus works best in radians, we do a lot of mental shifting back and forth between radians and degrees, because a lot of people are just better at thinking in degrees. I can visualize a 60-degree angle much more quickly than I can visualize its equivalent, a pi over 3 radian angle. But they're the same. We just have to get used to going back and forth between them. So this first question here is to evaluate cosine of pi over 3 without a calculator. So the way I would do that without a calculator, without using the unit circle, which we haven't talked about yet, is to draw a triangle. I'm going to draw the 30, 60, 90 triangle. And I do think of it as the 30, 60, 90 triangle. That's a 30-degree angle, that's a 60-degree angle, that's a 90-degree angle. And then the sides, and again, there's other ways of doing this. The sides I like to think of are the hypotenuse is always the biggest side, which is a length of 2. The side opposite the smallest angle is the smallest side with a length of 1. And the side opposite the medium angle is the medium length with a length of the square root of 3. Those are the sides that go with the 30, 60, 90 triangle. You might see other people do it the following way. Just so you know, other people might be like, hey, James, I prefer a smaller triangle. I prefer a triangle where the hypotenuse is 1. And then all the sides get divided by 2. So that's a 1, that's a 1/2, and that's a root 3 over 2. Also a perfectly fine similar triangle to the one that we have been talking about. You might use this one, you might use that one, you might use a different one. Some people like to use X's in there, kind of weird. Either way, whether I use this bigger triangle or this smaller triangle, I'm going to find cosine of pi over 3, which is cosine of 60 degrees. You can even write it's equal to cosine 60. One thing I will caution against is we should not say that this is equal to 60 degrees. Not equal to 60 degrees. It's equal to cosine of 60 degrees, which would be perfectly fine to write, although you don't need to. Either way, cosine of 60 is adjacent over hypotenuse, which is going to be 1 over 2. That's cosine of 60 degrees. Or that's cosine of pi over 3 radians. And that is how I would typically think about finding this trigonometric function of this particular angle, is by drawing a triangle. In a similar way, we could also ask, hey, what's sine of pi over 3? And sine of pi over 3 would be, well, 60 degrees is pi over 3. Sine is the adjacent, sorry, not the adjacent, so SOHCAHTOA, sine is the opposite of the hypotenuse, which is going to be the square root of 3 over 2. And usually, if I'm asked to find sine, cosine, tangent, secant, cosecant, cotangent of one of these special angles, pi over 3, pi over 4, pi over 6, thinking about the triangle is usually what I do. And then we kind of are going to extend that idea, I guess, next week on Monday when we talk about class V, because we're not going to do it on Friday. So what I want to talk about, though, is kind of leading up to that is some ways to visualize these other larger angles that we still consider to be special. So there's lots of quote unquote special angles, but it all really boils down to these three special angles: pi over 3, pi over 4, and pi over 6. But let's label them all on this not quite filled out completely unit circle and talk about them. And when I say that we have a unit circle here, the reason we call it a unit circle is because in the unit circle, the radius is equal to 1. That's why it's called the unit circle, because a unit is 1 in the real numbers. So not that we typically need to do this right now, but this point here, the right end point there, is the point 1, 0. And this endpoint on the y-axis is 0, 1. And this point over here on the left is -1, 0. And this point down here is 0, -1. And then we've got all these angles. And I should point out that when we talk about these angles, they're all measured from the positive x-axis in the counterclockwise direction. So when we measure angles, they are measured from the positive x-axis. So this part right here in the counterclockwise direction. So when I say that this angle here is pi over 6, what I'm really saying is the angle measured from the x-axis to there is pi over 6. And when I say that, use different colors here, I got green, I got green. All right, green. When I say that this angle is pi over 4, I'm saying the angle measured from the x-axis is pi over 4. Let's zoom in a little bit. And likewise, when I say this angle is pi over 3, I'm saying that this angle here measured from the x-axis is pi over 3. So we're always measuring from the positive x-axis in the counterclockwise direction. So we've got a lot of angles here, right? We've got pi over 6, pi over 4, pi over 3, and then at the end, we've got pi over 2, which is 90 degrees. I should say the end of the first quadrant, because this is the first quadrant. And then as we move into the next quadrant, the second quadrant, our angles get bigger. And what I really want to point out is, yeah, you've got 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. But here's what we actually care about. We care about how they measure to the x-axis. So even though I would say, and I don't really want to draw it because the picture looks nice and I want to like make it look ugly. Like if I was going to go from here all the way to there, that would be 2 pi over 3. What I'm really more interested in is what that angle there is. Well, it looks a lot like that angle there, which was pi over 3. And that's really what I want to know about. And similarly, this angle here from the x-axis to the angle 3 pi over 4 is pi over 4, which I know I didn't make look very nice there. And similarly, this angle measured from the x-axis to 5 pi over 6 is just pi over 6. Or in degrees, 2 pi over 3 is 120 degrees, 3 pi over 4 is 135 degrees, and 5 pi over 6 is 150 degrees. And these smaller angles are the difference to get to 180. So this pi over 6 is really 30. Well, we know what they are, right? We already said it. Pi over 6 is 30 degrees. Pi over 4 is 45 degrees. Pi over 3 is 60 degrees. So why do I care about these angles here? Well, they're what are called reference angles. Reference angles are the angle you get when you take like the terminus. So, okay, there's some language here that I don't really care that much about, that most people don't really care that much about, but I will use briefly here. This angle, like I'm looking at the angle 2 pi over 3, this ray, remember rays? I remember rays. They're the things that start at one point and go just in one direction. They're kind of like lines, they're like half a line. This ray is the terminal ray for that angle 2 pi over 3. This other angle here is the reference angle for that angle 2 pi over 3. It is the angle that gets you to the x-axis, is what I like to think of. And there's a really nice thing to see here, in that, especially if you write your angles in radians, one of the reasons we really love radians, reference angles are just kind of, you look at your angle and you say, get rid of the coefficient of pi. So for 2 pi over 3, the reference angle is pi over 3. For 3 pi over 4, the reference angle is pi over 4. For 5 pi over 6, the reference angle is pi over 6. Now I'm going to point out, this only works for the special angles. We talk about other angles, it does not work like this. You have to work hard, and we're going to talk about it in just a minute. But the special angles, it's beautiful. You get this really, really nice thing that happens all the time. So let's write out the other special angles in quadrants 3 and 4. So in quadrant 3, so if I go pi over 6 in this direction, I'm going to take pi and add pi over 6, which is going to get me 7 pi over 6. Or if you prefer degrees, 210 degrees. I just added 30 degrees to 180 degrees. And if I go down to the next special angle, which I'm disagree, I wish this pen worked a little bit better, but it doesn't. If I go that way, if I add pi over 4, well, pi plus pi over 4 is 5 pi over 4. And in degrees, that's going to be 225 degrees. And finally, not finally, nextly, this reference angle here is pi over 3. The angle there is pi plus pi over 3, which is 4 pi over 3. Or if you like degrees, 180 degrees plus 60 degrees is 240 degrees. But again, what I want everyone to see here is that the angle 4 pi over 3 has a reference angle of pi over 3. Because if you measure back to the nearest x, I'm going to emphasize x-axis, you get the angle pi over 3. 5 pi over 4 has a reference angle of pi over 4. 7 pi over 6 has a reference angle of pi over 6. And then finally, in quadrant 4, the same sort of thing is going to happen. Let's do it this way. So I'm not going to do 0 minus pi over 3. I'm not going to say that this angle is negative pi over 3, although you wouldn't be wrong to say that. We're thinking of our angles being between 0 and 2 pi in this one revolution of a unit circle. So if I take 2 pi and I subtract pi over 3, I'm going to get 5 pi over 3. And if I take 2 pi and subtract pi over 4, I'm going to get 7 pi over 4. And if I take 2 pi and subtract pi over 3, I'm going to get, let's see, 6 pi over 3 minus pi over 3. Sorry, not pi over 3. I said the wrong thing. Pi over 6, apologies. If I take 2 pi and subtract pi over 6, that's going to be 12 pi over 6 minus pi over 6, which is 11 pi over 6. Or in radians, or sorry, in degrees, we have 330 degrees. Here in degrees, we have 315 degrees. And here in degrees, we have 360 minus 60 is 300 degrees. So these are all the special important angles on the unit circle. I guess we didn't talk about the ones at the corners. I call them corners. I know it's terrible. I do call the top, bottom, left, right, the corners of the circle, because it's so much easier than saying like the north, east, south, and west of the circle, or the 4 cardinal directions of the circle. But you can say the top, bottom, left, right. So this angle here is pi over 2, which is 90 degrees. This angle is pi, which is equal to 180 degrees. This angle is 3 pi over 2, which is equal to 270 degrees. And this angle is 0 or 2 pi, which is 0 degrees or 360 degrees. So there is our filled in with all the angles unit circle. Now, we still haven't talked about the values yet, and that's a story for next class. Well, the next class where we learn something new, which is on Monday. So Monday we'll talk about the values, but for now we're just dealing with the angles. So I'm going to interject an extra page here. Sorry, I meant to give you an extra page in your notes and then totally forgot to do it. So I would say use the back of this page to write some reference angle stuff here. Did I give myself more pages? Thought I did. There we go. Yeah, extra pages. So reference angles. People kind of, I don't know, in the past, I feel like people have just kind of assumed that it's a known thing, but I do want everyone to know what a reference angle is. So reference angle is an angle. No surprise there. So it's an angle between 0 and 90 degrees. Or if you prefer radians, between 0 and pi over 2 radians. That is the angle we get when we measure from, I'm going to use the term again, the terminal ray to the nearest x-axis. Always the x-axis, never the y-axis. So in our previous stuff we were doing, it's just all the angles we talked about. But we could talk about other examples. And where's my picture that I want to look at? Yeah, cool. So papers, sorry. So for example, what's the reference angle for, say, the angle theta equal to 140 degrees? Well, I just want to find the angle I would get if I measured to the nearest x-axis. So I'm going to draw this angle in the standard way. Here's how we do that. I'm going to draw it as, I'm going to start at the positive x-axis and go 140 degrees. So let me ask you all to show me on your fingers. What quadrant is our angle going to terminate in? Is it going to be quadrant 1, 2, 3, or 4? Yeah, exactly. Quadrant 2, because it's bigger than 90, but not as big as 180. So we're going to quadrant 4. And I'm not, or quadrant 2. I'm not going to draw it perfectly. I don't really care, but it looks something like that. There's my 140 degree angle. And the reference angle is what you get. I like to think of it as when you drop a perpendicular to the x-axis. So if I kind of take this and drop a perpendicular here, there's my reference angle. It's how much I need to get all the way to the x-axis. Either how much I have to add on to 140 to get to 180, or if my angle was in quadrant 3, how much I might have to subtract off to get to 180. In this case, my reference angle is going to be 40 degrees. So here the reference angle is equal to, the way I'm thinking of it is, it's the difference between 180 degrees and 140 degrees, which is 40 degrees. Cool. I should point out, your reference angle can never be actually equal to 0 degrees. It has to be strictly bigger than 0 degrees and strictly less than 90 degrees. It cannot ever equal either of those two things. It also can't ever be negative. Reference angles have to be positive angles. I should say, really, they have to be acute angles. Acute angles are angles that are between 0 and 90 degrees. Let's look at a couple more examples just to make sure we're on the same page. So let's say our example was theta equal to 265 degrees, which, again, show me on your fingers, what quadrant are we landing in with that angle? Yeah, right. We're almost to quadrant 4, but not quite, because quadrant 3, I should say the line between quadrant 3 and quadrant 4 is 270 degrees, or the angle that separates quadrant 3 and quadrant 4 is 270 degrees. So our angle is almost there, but not quite all the way there. It's 265 degrees. Now be careful. The reference angle is not 5 degrees. Right? It's not how much we get when we measure to the y-axis. It's always, always, always measured to the x-axis. So I'm gonna measure back to the x-axis. Really, I'm just gonna draw it here. There is my reference angle, measured from my terminal ray to my x-axis. So it's, in this case, not how much, well, it's still the difference. The only difference with this difference is that in the one before I did 180 minus 140, here I'm going to have to do 265 minus 180 to find my reference angle. And that's going to be 265 minus 180 is 85 degrees. We could also do it if our angle was measured in radians. Now, here's the thing about radians. It's going to be a little bit harder to tell what quadrant your angle lives in at first. So let's look at an example. Do I have one written down? Probably not. If not, that's fine. Maybe I have one on the next page here. Let's take a look. Sorry. 1 second. Oh, yeah. Let's say our angle was, let's not do that one. Let's do, sure. Yeah, that's a good one. Let's say our angle was theta equal to 12 pi over 7. Ugh. All right. So now what quadrant does that one live in? Well, shoot. I know it's bigger than pi, right? It's definitely bigger than pi because 12 over 7 is bigger than 1. So it's certainly not in quadrant 1 or 2. It might be quadrant 3. It might be quadrant 4. I think it's quadrant 4. How do we tell? Well, how do we tell? It's a good question. I often kind of ignore it, to be honest, but if we really wanted to tell, you could say, well, I'm looking to see if I'm going to end up being bigger than 3 pi over 2 or smaller than 3 pi over 2. So let's compare them. I need the common denominator. So 12 pi over 7, if I multiply that by 2 over 2, 12 pi over 7 times 2 over 2 is 24 pi over 14. And 3 pi over 2 times 7 over 7 is 21 pi over 14. So this one is bigger, which means the angle is going to go further than that 3 pi over 2. But it's not quite as big as 2 pi, because 24 over 14 is definitely not as big as 2. So there's my angle, 12 pi over 7. And I want to find my reference angle. So I want to find how much I need to get all the way back around to 2 pi radians. So just like in the previous ones, I'm just finding the difference between my two angles, between the angle I have and the angle I'm on, the x-axis angle I am measuring to. So in this case, my reference angle is going to be 2 pi minus 12 pi over 7, which is going to be, let's see, I get a common denominator, 14 pi over 7 minus 12 pi over 7 is equal to 2 pi over 7. And you kind of have to write your answer this way because if you try to change this one to degrees, you get like a decimal thing that doesn't ever terminate. It's not a nice number. It's not like how 30 degrees is pi over 6. So for this one, you really kind of have to leave it in radians. And the thing I wanted you to see with this one is, right, if my angle is 12 pi over 7, my reference angle isn't just pi over 7. Right? We actually have to work a little bit harder. It's not like our nice special angles from our unit circle, where if your angle is 5 pi over 3, your reference angle is just 1 pi over 3. Or if your angle is 5 pi over 4, your reference angle is 1 pi over 4. For these ones, it always works out this nice way where your reference angle is just 1 times pi over whatever the denominator already was. It's a kind of cool trick. For other radian angles, though, your reference angle is usually more complicated. I want to throw one more in there, make it fit in here. One more example. So let's say, and I'll let you all do this. Oops, I'll let you all see this one maybe. Let's say your angle was, what have I got here? I got you, you're fine. Let's say your angle was 13 pi over 9. I would like all of you to try to figure out which quadrant that angle is in. And then after you figure out which quadrant, or maybe even not after, and then determine what the reference angle is going to be. Trying to get my notes more together here. Pretty sure it's in quadrant 3. I'm 100% sure. Well, let's say we didn't want to think too hard about what quadrant that angle was actually in. Remember, I'm not going to think about it at all, really. We're going to do instead, well, we're going to think about it a little bit. So 13 pi over 9 is definitely, wow, that pen's terrible. Sorry. 13 pi over 9 is definitely bigger than pi. Because it's 13/9 of pi. And 13 pi over 9 is definitely smaller than 2 pi. Because 2 pi would be 18/9 pi if I was getting a common there. So we're pretty sure, we're very sure, that we're either in quadrant 3 or quadrant 4. And our angle is doing something, but we're not quite sure if we stop like here or maybe we stop like there. Here's a way you can figure it out without having to actually, if you've got it narrowed down to 2 quadrants. Here's something you can do instead. So I'm going to say, well, what if it was in quadrant 4? Even though I know it's not. But if it was in quadrant 4, the way I would find the reference angle is I would find the difference to the nearest x-axis. And the nearest x-axis in quadrant 4 has an angle of 2 pi. So if I do the subtraction there, I'm going to get 2 pi minus 13 pi over 9, which getting a common denominator is going to be 18 pi over 9 minus 13 pi over 9, which is 5 pi over 9. Okay. Now, one of two things can happen here. You can either say, well, I'm not sure if that's too big or not, so I'm going to find the other possible answer. Or you can say, that's too big. 5 pi over 9, 5/9 is bigger than a half. Say that again, 5/9 is bigger than 1/2, right? Because it's bigger than 5/10. So 5/9 is bigger than a half, 5 pi over 9 is bigger than pi over 2, which is 90 degrees. That angle is too big to be a reference angle. Because really our angle was in quadrant 3. And if we do the work to find the reference angle, thinking it's in quadrant 3, we're going to do our angle minus pi. So we're going to do 13 pi over 9 minus pi, which is 13 pi over 9 minus 9 pi over 9, which is 4 pi over 9. And that is definitely the smaller of the two, and it is the one that is smaller than 90 degrees, or smaller than pi over 2 radians. This is definitely our reference angle here, and that is not. So that's another way you can think about it. You can kind of think, well, I know it's in quadrant 3 or quadrant 4. If I find both possible quote unquote reference angles, then whichever one is the smaller one is your actual reference angle, and the bigger one is just garbage. So reference angles in a nutshell, you're always finding the angle you get from where your angle ends measured to the closest x-axis. So if you're in quadrant 2 or quadrant 3, you're measuring to 180 degrees or pi radians. If you're in quadrant 4, you're measuring to 2 pi radians. If you're in quadrant 1, it's just the angle you've already got, assuming you have, right, you're not like doing angles that are bigger than a whole revolution, which we'll talk about later. Okay, so the reason we're talking about these reference angles is because then we use them to find sine, cosine, tangent, secant, cosecant, cotangent of angles that are other than our special angles, but have the same reference angle as our special angles. Here's what I mean. Let's look at this next example. All right. So since we know, or have maybe know is a strong statement, since we have seen all the trig values for pi over 3, pi over 4, and pi over 6, we can use those values to help us find the trig values for angles that are I'm sure multiples of pi over 3, pi over 4, pi over 6, but really angles that have pi over 3 or pi over 4 or pi over 6 as their reference angle, because they're going to have the same value, which is kind of cool. So here's the idea. I want to find sine of 5 pi over 3. So what I'm going to do first is any cosine of 5 pi over 3. Step 1, find the reference angle. Now we could do the work, and I'm going to show the work, even though from what we said on page 1 today, we can all kind of make a good guess that the reference angle should just be 1 pi over 3. Let's draw it though. It's good to draw. So if I draw my angle, 5 pi over 3 is going to end up in quadrant 4. Here's my terminal ray. Here's my angle, 5 pi over 3. Oh, sorry, I'm still zoomed in. That's fine. And then here's my reference angle. The rest of the way to 2 pi. So my reference angle here is going to equal 2 pi minus 5 pi over 3, which is 6 pi over 3 minus 5 pi over 3, which is, as expected, 1 pi over 3. Or if you prefer, 60 degrees. Something I was going to say here. Oh, I know what I was going to say. If you happen to do the subtraction in the wrong direction, like if you did 5 pi over 3 minus 2 pi and got negative pi over 3, that should be a good indication that, oh, if I got a negative answer, but it's still an angle that looks like a reference angle, your answer should just be positive, and we should do the subtraction in the other order. But you could probably be like, oh, well, I know it's going to be positive pi over 3. And you probably don't need to actually do more work. So then find the reference angle. Oh, sorry. Thing 2, maybe these should be in the opposite order, but I said them in this order, so I did. Identify the quadrant that the angle terminates in. In this case, the quadrant is, well, we can see it, we drew it, it's quadrant 4. And again, it's harder to see if your angle is measured in radians. It's much easier, we have a much better intuition to be like, oh, 300 degrees, of course it's in quadrant 4, because it's bigger than 270 and smaller than 360. But I would encourage you all, when you're doing these problems, if they're written in radians, try to think of it in radians and try to figure out which quadrant it's in radians, even though it might be easier to do in radians for you. I would encourage you to try doing it in radians, because people are going to throw radians at you as your math future goes on. So in this case, the quadrant we are in is quadrant 4. Okay, the third thing we're going to do is we're going to find the, whatever in here exactly, yeah. So find the values for your trig functions using the special angles. Or the special triangles, I should say, yeah. Using special triangles for the reference angle. So our reference angle is pi over 3. So I'm going to use, and I know we already did pi over 3 earlier, but we're going to use pi over 3 to find what sine of pi over 3 and cosine of pi over 3. Now I know that's not the same thing as what we're actually being asked to find. That's okay. So here's my special triangle once again. My 30, 60, 90 triangle, or my pi over 6, which is 30 degrees, my pi over 3, which is 60 degrees, holy smokes, and my 90-degree angle, which is pi over 2. And then my biggest side is 2, my smallest side opposite my smallest angle is 1, and my medium side opposite my medium angle is square root of 2. Great. So looking at this, I can see that sine of pi over 3 is the opposite of hypotenuse, which is square root of 3 over 2.
And cosine of pi over 3. The shadow is kind of terrible here. Sorry about that. My hand, I know it's terrible, is 1/2. All right, so here's the last part, which is kind of the new part. We're going to then find the actual trig functions of the given angle based on the sine, SIGN, of your trig functions, which is based on the quadrant that we're in. Okay, so here's the deal, and this is kind of something this is the piece of information that is new, at least for some of us, maybe. Here's quadrant 1, here's quadrant 2, here's quadrant 3, here's quadrant 4. I'm going to tell you a thing, and we're going to kind of see how it's true a little later. But here's what I'll tell you for now. In quadrant 1, all of our trig functions are positive. Sine, cosine, tangent are all positive because all the angles are acute. Whereas in quadrant 2, sine is positive. And cosine and tangent are both negative. In quadrant 3, tangent is positive and the other two are negative. And in quadrant 4, yep, exactly, she's saying it. There are other ways of saying it too. In quadrant 4, cosine is positive and the other two are negative. And as someone has said, one way of remembering this is all students take calculus. So our angle is in quadrant 4. And in quadrant 4, cosine happens to be positive and sine happens to be negative. So if I want to find sine of 5 pi over 3, it's going to equal negative root 3 over 2. If I want to find cosine of 5 pi over 3, it's going to equal positive 1/2. And that's kind of the fast way of doing it. But let me show you a slightly longer explanation because I think it's worth your while. So here's what we're actually kind of doing. We're taking our special triangle, whose reference angle is pi over 3. And what we're kind of doing is we're actually just taking it and flipping it over and turning it around and putting it right there. So that, check this out. This angle, the reference angle, is the angle we want it to be, the angle we're trying to find sine, cosine, tangent of. Pi over 3 in this case. And now if I think about the sides of my triangle, well, they're still the same lengths, but if we're in the XY coordinate system, if you go to the right, it's a positive X value. But if you go down, it's a negative Y value. And if you go out from the origin, we kind of think of this as a radius. That's always going to be a positive hypotenuse value. So look here. If we think about cosine of pi over 3, it's adjacent of our hypotenuse, which is positive 1 over 2. We think about sine of pi, we think about cosine of 5 pi over 3, it's adjacent of our hypotenuse, which is 1 over 2. We think about sine of 5 pi over 3, it's opposite of our hypotenuse, which is negative root 3 over 2. So because in quadrant 4, the y part is negative and the x part is positive, cosine ends up being positive and sine ends up being negative. But it's much easier to not draw this picture every time and think about how the triangle lands there. It's much easier to be like, oh, I know the reference angle. I know the special triangle for the reference angle. And then I can determine the SIGN sign of my sine or cosine. It's terrible to sound the same. Just based on what quadrant we're in. So that's kind of, in my opinion, the fastest way of doing it. Now, it still might not seem very fast, or I should say, right? There's definitely a faster way to use a calculator. But this is the fastest way of doing it without having to use any extra means. Let's look at a couple more examples. Let's keep things in order. Sure. So, yeah. Time is it? Okay, let's run short on time. That's all right. So if I want to find sine, cosine, and tangent of 7 pi over 6, I'm going to do the three things. Thing one, my reference angle is definitely pi over 6 because it's one of these special angles. Thing two, what quadrant are we in? Well, let's see. 7 pi over 6 is just a tiny bit bigger than pi, right? It's actually literally 1 pi over 6 bigger than 1 whole pi. So I'm just slightly into the third quadrant. There's pi, and there's another pi over 6. We're in quadrant 3. Okay, what's next? Oh yeah, use my special triangles. So here's my special triangle. It's the same one. Excuse me, it's the same one as before. I drew it in the opposite kind of orientation because I like the angle I'm looking at to be in the lower left corner. My own personal bias. So now the biggest side is still 2. The side opposite the smallest angle is still 1, and the side opposite the medium angle is still square root of 3. And I can see that. So watch how I write this down because I do think it's worth noting. I can see that sine of pi over 6 is positive 1/2. Cosine of pi over 6 is positive root 3 over 2. And tangent of pi over 6 is opposite adjacent, which is 1 over root 3, which rationalizes as root 3 over 3. Now, those aren't the answers to my question, but they are worth knowing. So then, based on the fact that we are in quadrant 3, and the fact that all students take calculus, we know that tangent is going to be positive, and both sine and cosine are going to be negative. So we're going to say that sine of 7 pi over 6 is negative 1/2. Cosine of 7 pi over 6 is negative root 3 over 2. And tangent of 7 pi over 6 is positive. You don't have to write the positive, but I kind of like to write it because it really emphasizes the fact that we know which ones are negative and which ones are positive. Positive root 3 over 3. Again, if you were to take your special triangle and plop it down in the third quadrant so that that reference angle was there, it would look like this. Where this side is 2, this side, well, if I'm going down, it's negative 1. If I'm going left, it's negative root 3. So yeah, it makes sense that cosine would be negative because it's adjacent of hypotenuse, and sine would be negative because it's opposite of hypotenuse, but tangent's going to be positive because it's opposite over adjacent, which is a negative over a negative, which is a positive. But again, I don't think you need to do that, right? We can use kind of the shortcut to say, oh, yeah, I know if I'm in quadrant 3, tangent's positive, and it's for negative. Let's look at one more. Yeah, time's a wasting here. So I want to find secant of 3 pi over 4. I really don't want to find secant of 3 pi over 4. I want to find cosine of 3 pi over 4. If I'm ever faced with finding one of the reciprocal functions, secant, cosecant, or cotangent, I'm always going to find its reciprocal first. So first I'm going to think about actually finding cosine of 3 pi over 4. And then at the end, I'll find its reciprocal. So thing one, my reference angle is pi over 4. Thing two, we're in quadrant 2 because we're definitely less than a whole pi, but bigger than pi over 2. We're looking like this. And then thing 3, cosine of pi over 4 is kind of my favorite. You know, the cosine and sine are the same. Cosine of pi over 4 is, oh, I didn't draw the triangle. I'm getting ahead of myself. Eventually, the idea is you don't have to draw the triangle. You've just done it so many times, you've memorized it. But drawing the triangle is how we would do this. So if I was drawing the triangle, I would have my 45, 45, 90 triangle, or my pi over 4, pi over 4, pi over 2 triangle, which has sides 1, 1, and root 2. So cosine of pi over 4 is 1 over root 2, which we rationalize as root 2 over 2. And then second to finally, cosine of 3 pi over 4. Well, since we're in quadrant 2, where sine is positive, cosine is going to have to be negative. root 2 over 2. And then finally, secant of 3 pi over 4 is the reciprocal of this. Now I should point out, it would have been easier for me if I thought ahead of time about taking the reciprocal to have written it as 1 over root 2, because the reciprocal of 1 over root 2 is much easier to do. The reciprocal of negative 1 over root 2 is negative root 2 over 1, which is just negative root 2. I should mention here, reciprocals always retain the same positive or negative sign. If your thing is negative, its reciprocal is negative. If your thing is positive, your reciprocal is positive. So even though we only talk about how all students take calculus to tell us if all things are positive or sine's positive, tan's positive, cosine's positive, when I say this, when I say that sine is positive, I'm also thinking, oh yeah, its reciprocal is also positive here. Cosecant is positive in quadrant 2. Cotangent is positive in quadrant 3. Secant is positive in quadrant 4. And the reciprocals of the other things are negative by the same kind of idea. Yeah, never enough time. Okay, so one more thing. Well, not one more thing. Never just one more thing. Fine. I know I'm a tiny bit fast here. Apologies. I do want to get to one example of this last type. So we already kind of talked about this, but I'm going to say it again. As far as the sign of your trig functions go, in fact, we've said it a million times already, it's this whole all students take calculus thing. If you want a less PG version of that, come see me in office hours. I'll tell you another version of it. It's more fun to say, but refrain from saying it in class. So we have all students take calculus. And all this means is that in this one, right, all trig functions are positive. Sine, cosine, tangent, secant, cosecant, cotangent, all positive. Here, sine is positive and the other two are negative. Now I'm going to say again, cosine's negative, tangent's negative. And we extend this idea to the reciprocals. So in quadrant 2, cosecant is also positive, secant and cotangent are also negative. But we don't write them down because it's just no. In quadrant 3, tangent's positive, cotangent's also positive, sine and cosine are both negative. Secant and cosecant are both, I should say cosecant and secant are both negative. And then finally in quadrant 4, cosine is positive, sine and tangent are both negative. And all their reciprocals. Okay, I do want to throw one last example at you because sometimes we ask things like the following. What if we aren't given the angle, but we still are asked to find sine or cosine or tangent of the angle? For example, if sine of theta equals negative 3/5, if sine of theta is negative, what quadrants could we be in? Could we be in quadrant 1? 3, definitely. What other quadrant is also an option? I didn't quite hear you. Yeah, exactly. If sine's negative, that immediately limits us to either quadrant 3 or quadrant 4. And if tangent's positive, that limits us to quadrant 1 or quadrant 3. But quadrant 1's out because sine's negative. And I guess quadrant 4 is out because tangent's positive. So these two pieces of information tell us exactly what quadrant we're in. We have to be in quadrant 3. And then I want to find cosine of this angle. So here's what we do. We take our sine value and we draw some stuff. Yeah, I can draw this thing. Sure. So I would probably just do this, to be honest. I would say, I don't care about the negative sign for a second. There's theta. If sine of theta is 3/5, ignore it. Yeah, if you need to go, please go. If sine of theta is 3/5, ignoring the negative sign. Sine is which side over which side? So, right, opposite over hypotenuse. So sine is opposite over hypotenuse. And I'm thinking of my opposite as 3 and my hypotenuse as 5. And then we can use the Pythagorean theorem to find the unknown side. This unknown side, x squared plus 3 squared equals 5 squared. x squared equals 25 minus 9, which is 16. So x is equal to 4. So then cosine is adjacent over hypotenuse. So I can say that cosine of theta is 4/5. Except what quadrant is our angle in? Quadrant 3, and in quadrant 3 is cosine positive or is cosine negative? Definitely negative. So really we get cosine theta equal to negative 4/5. The other way of doing this, if you prefer, although I think this is the better way of doing it, is you can draw your triangle in the appropriate quadrant. So you can say, I'm going to draw my triangle like this, where that's my angle there, and then that's a negative 3/5, and that's a negative 4, and then you can find cosine that way. I don't like that as much, but some people really do, so if you want to do it that way, you can. I didn't get to the last page, so I'll stop there. There is one more example on the last page. It's definitely in the notes. You should look at it if you want, because there definitely are a couple homework questions like this on the homework, so I'll say about that. All right, Friday we'll review. I guess I should clarify which of the things I posted we'll review. I will do that today via an announcement, and then you'll have the midterm over the weekend. As usual, I'm fairly available. I encourage you to take the midterm. If you think you might need to reach out to me during like the middle parts of the day, because I am usually going to bed 9:30-ish, because I'm an old person. So if you're taking your midterm at like 10 o'clock, you might not be able to get a hold of me. Nothing should go wrong, but if something goes wrong and you want to be able to get a hold of me, take it during the daylight hours. Well, daylight, okay, daylight's is strong, but take it during the James is awake hours. Daylight's okay. I don't go to bed at 5, right? Okay. Not yet, anyway. Not that way. Let's see here. That's. You too. I feel like I'm missing a page. No, the first page. Where'd the first page go? How's it going, Maggie?
How to convert 10 radians to pi?
Yeah. So how do you, so what do we always multiply radians by to get to degrees? Okay, so let me ask you this question. Well, let's see. So if let's say I had like 2 pi over 3. And I want to end up with degrees, right?
Yeah.
So we're going from radians to degrees.
180 over.
Right, because the thing you want should be the unit that's on top.
Yeah.
And then the pi's cancel because it's a nice angle in radians and you get 120 degrees. But if you have 10 radians, you're still going to multiply by 180 over pi. 180 degrees over pi.
1000.
Right, so your not very nice answer.
Or 1000.
Now you could use a calculator to get a decimal approximation, but this is kind of the exact answer. If you do 1080 divided by pi, you're going to get something in the neighborhood of 300 degrees. That seems wrong. Think about this right now. 10 radians should be more than the whole. I'm not good at division, apparently. 1000 divided by 3 it'd be like, I don't know. I feel like I'm making a mistake of some sort here, but I guess not. I don't know. I guess I have a calculator. I can figure it out. Let's see if we do 1080 divided by 3.
We love one
Divided by pi. So 3. It's 343 degrees. It doesn't feel right. It feels wrong. To me.
It feels wrong.
It does feel wrong.
That feels weird.
It feels really wrong. Oh, because I did the math wrong. You see my mistake? Yeah.
1800.
There we go.
There, I was like, wait, where's
It should be more like 600 degrees.
Boo.
500 something degrees. So I would, if I was writing my answer, I would write this,
Oh,
and then I would write. It's and then I'd say it's approximately equal to whatever.
sounds like a 71. I think it's
Sure, yeah, that sounds about right. That's the idea. Now, and also, I mean, the instructions might be specific, it might say, give us a decimal approximation or leave it as an exact answer.
Okay, so we were like, it's gonna be 1,008.
Right. Yeah, so sometimes there's radian measures that are not nice. If your radian measure doesn't have a pi in it, it's not gonna have a nice simplification, right? A nice degree. It's gonna be some